Yeah. Okay. So the last presentation, yeah, it's a little difference from the first two talks. Yeah. Okay. So, hi everyone. My name is Chao Xia. Yeah, I'm now doing my postdoc in Chalmers University of Technology. But this work was done at last year when I was in Tongji University, and it was collaborated with Shanghai Dr. Zhou from Shanghai Volkswagen. Okay, so the topic is about the augmentation of the RANS model using field inversion and machine learning that applied to automotive aerodynamics. So I will introduce from these four aspects. So as we all know that the RANS model usually struggle with accuracy when it simulating the large separation flow. Yeah, so for example, the Windsor-body. Yeah, so the main reason is that the RANS model make many assumptions and simplification, and their coefficients are usually calibrated by very simple flow. So recently, that the data-driven and machine learning method have made a very rapid progress and started to try to enhance the RANS model accuracy. So I think one of the standout methods is this one, the field inversion and the machine learning. Actually, this method consists of two steps. So the first step is it called the field inversion. So for example, in IC model that a correction factor beta is added to the production term, then and like it's similarly like a data simulation that an optimization problem is solved, aiming to like minimize the difference between the RANS simulation and the high fidelity data like DNS, LES, or maybe experiment data. So after this first step, then the second step is the machine learning, that we will train a model to link the local flow feature to the optimal correction factor. So after getting this model, then this model is feedback into a simulation, and all to other cases to try to enhance the accuracy of the RANS model. So since this method have been proposed, it has been applied to many simple flows, especially for the 2D flows, with very good results in improving the RANS model's accuracy. But until now, that I think this method, the FIML method, its suitability in like the very complex 3D flow, those flow around a car is still not unclear. So in this work, we made a very initial attempt to use this FIML for the GEKO model, to the GEKO simulation for the Windsor-body. So we know that the GEKO model is a generalized K omega model in ANSYS Fluent. It has 6 free parameters, yeah, and it can be implemented by these 3 F functions, which can be like tuned by a user to achieve different goals. So I will not give very detailed about the parameters, but I think for our flow around a car, the most important parameter is the CSAT and the CMix. So this slide shows the flow chart of the FIML method we use. We use the experiment data as a target, and for the field inversion part, so the first part, we will use a joint method to like to the GEKO CSAP and CMix. aiming to like minimize the difference between the RANS simulation and the experimental data for like CD or base pressure or the velocity in the wake. And then for machine learning part, that we use the artificial neural network. So here list the activation function and the hyperparameters. And the number that training samples is essentially the number of the grid points we used. Now let's look at the results. So the mesh that we generate is infinite mesh, similar with the G2 baseline, and we use a pressure-based coupled solver, the 2-second augment scheme. Okay, so here I show that the comparison between 4 cases. So the first, these 4 cases have a different like the targets for the targets from experiment for field inversion. So the first one is we use the total CV from the experiment. The second one is use the CB, that is the base drive. So the third one that we use the CP of 38 pressure types on the base. And the last one that we use stream-wise velocity of 15 points in this horizontal slice. Okay, so here shows the results. So we can see for the CD prediction that the baseline flow is with original GEKO model. So it had I think it's about 30 counts smaller than the experiment. And also for the base drive, it's about 35 counts smaller than the experiment. But we can see that after this field inversion, the yellow ones, so all the cases can get a CD very close to the experiment than the baseline. Especially for the first 2 cases, the target CD and the target CB or the target base CP. And also for, I think for the base drive, it looks like the second case and the first case match the experiment better. But they all, I think, have a significant improvement than the baseline. And then we look at the blue one, it's a machine learning model. We can see that except for the third case, that all the other cases can get very close the value with their corresponding field inversion. Next, let's move on to the base pressure and the wake. So we can see the left is the base pressure that compared to the baseline flow, we can see that all the 4 cases that after field inversion, they can predict the flow, the pressure, the asymmetric pressure that's better than the baseline, especially this case that targets the wake, the UX. It's very similar to experiment than baseline. And also for the right figure is velocity streamlines. We can see the velocity streamlines are also consistent with the base pressure distributions. So for this case, the target wake UX, it both can predict the length of the recirculation bubble and also asymmetric vortex structures. It's very similar to the experiment. But for these 2 cases, the target CB or CB, we can see that the length of the recirculation bubble is okay. I think it's better than baseline, but they failed to capture this flow asymmetry. And we also check the GEKO coefficients, the C7 and the C-mix. So for the baseline flow, the C7 and the C-mix are both constant. But after field inversion, that we can see that the C-SAP and the C-mix many changes in the left or right shear layer, especially for the last case that targets a weak UX. It has a very complicated the C-SAP and C-mix distribution, and with a clearly asymmetry from left and right. So this leads to a very noticeable change for the ID viscosity. And because usually that we increase in the C mix will leading to a larger ID viscosity. It means that a more stronger mixing in the shear layer and leading to a shorter recirculation bubble. Okay. Oh, sorry. And this slide shows the machine learning results, for the C-SAP and C-mix. So I think all the cases can overall they can predict the distribution of the C-SAP and the C-mix. But I think that for these two cases, especially the last case, we can compare with the field inversion results. They show a little discrepancy from the field inversion results. I guess it's caused. It's because that now I just use a very a small neural network to try to capture and the same one for all these cases. So maybe we increasing the hidden layers and the nodes of a neural network can be perform better, but it needs to be further studied. So anyway, that's we conducted a preliminary like a generalization for the GEKO model that we trained by the first case, the target CD. We applied this trained GEKO model for the full-scale drive speed bike. So we can see that for the baseline flow, the CD is I think is around about 20 counts smaller than the experiment. But if we use the trained GEKO model with the Windsor-body that we use this model, we can see the CD will very close to the experiment. And also you can see the very noticeable weak change in the flow. But now I think the flow field still need to be further validated by the experiment data. Okay, so I think this shows that the trained GEKO model maybe have a little generalization like ability. Okay, so finally the conclusions that this work that we made a very initial attempt to use this field inversion and machine learning method to try to enhance the GEKO RANS model. Yeah, we can see that when we for the field inversion part, when we use the CP on the base or the UX in the wake as a target for the field inversion, it can get a base pressure and also the wake flow are closer to experiment than using the CD or CB. And the field inversion can optimize the GEKO, the C-SAP or C-mix of the shear layer. It changing the turbulent viscosity and making the flow or the CD and the CB more consistent with experiments. And from machine learning part, the artificial neural network can be able to link the flow features to C-SAP C-mix, but the effect of the neural network topology, I think it needed to be further studied to improve its generalization. Okay, that's all I can show. Thank you.